Hello everyone, my name is Bhargav. I am here again to discuss assignment 6 solutions of this course Quantum Information and Computing. So let us begin with first question. So the question says, in a classical 3-bit error code, the string is received as 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 1, 0, 0, 0 and 1, 0, 1. Now divide this code into chunks of 3 bits. So as following majority principle, this 3-bit code is decoded as 0. As we have two ones here, it is decoded as 1. Similarly, others 0, 1, 0, 1. So the actual So in reality, this message is 0, 1, 0, 1, 0, 1. So correct option is option A. Let us look at question 2. Question 2 says, in a 3-qubit code, assume that the probability of a single bit flip error is 0.05. So probability of error in a single bit is 0.05. It is also given that ancilla bits are measured as 0, 0. In the lecture notes 31, you can find which ancilla bits corresponds to which state. So taking reference from the notes, we see that we get 0, 0 as ancilla bits if the state is either 0, 0, 0, 1, 1, 1 or the reverse. So the other state is this is a error free state, and this is a state where every bit has an error in it. So probability of occurring this state is 1 minus p cube, and probability of this state occurrence is p cube. As every bit has error and there are 3 bits, probability of error is 0.05, which is p. So having these two events, probability of occurring of this event is 1 minus p cube divided by 1 minus p cube plus p cube, which is 0.95 whole cube divided by 0.95 whole cube plus 0.05 whole cube, which is 0.999854, so on. From the given options, nearby answer is 0.99985. So the correct option is C. So in the question 3, we see that probability of error happening is 0.05, and also given that ancilla bits are measured to be 0, 1. and corrective measures are taken appropriately. So the ancilla bits are 0, 1. From note 31 we see that these ancilla bits happens if only the state is 0, 0, 1, 1, 1, 0, or the state might be so probability of occurrence of first state is there is only one error, so p times 2 bits are error free, so 1 minus p square. In the second case there are 2 errors, so p square, and 1 error free, so p square times 1 minus p. So error corrections are taken as if we have obtained the first state. So the second state completely goes into the error thing. So to obtain a error free output, we should be getting this state which has a probability of p times 1 minus p whole square. So the final probability of obtaining this state is p times 1 minus p square divided by p times 1 minus p square plus p square times 1 minus p, which is we can cancel p times 1 minus p in the numerator and denominator. So you obtain plus p, which is nothing but 1 minus p. As p is given as 0.05, the final answer is 0.95. So the correct answer is option B. So in the question 4, we are asked in which of the cases we do not need to take any corrective action. The corrective action is based on ancilla bits. So let us look at the corresponding ancilla bits. So the received message are given as corresponding ancilla bits are 1, 1. You can see these correspondence from notes 31, lecture notes 31, and option B is A110 plus B001. Corresponding ancilla bits are 0, 1. Corresponding ancilla bits are 0, 0. Option D A100 B011. Corresponding ancilla bits are 1, 1. We always takes corrective action unless the ancilla bits are 0, 0. So this state, if we obtain this state, we do not take any corrective action. So correct option is option C. The question 5, it states as in the question 5 we are using 3-bit classical code, and it is given that probability of a bit flip is 1 by 10, that is 0.1, and the question asks what is the probability of getting an error free message in a protocol that uses majority vote. Like majority vote is like if you have obtained 1, 0, 1, as you have 3 bits and 2 out of them are equal to 1, the actual state is 1. So let us solve this question. So probability of bit flip is 1 by 10, that is equal to 0.1. So say we have 3 bits, and we want them, and we want 2 of them at least. We either want all of them to be equal or at least 2 of them to be equal. So the probability of having all of them equal and they should be equal to the actual correct bit. Say correct bit is x, then you need to have the code x x x or x x y. This y can happen in any position. So the probability of the first event is 1 minus p cube. Say the error of bit flip is p, then 1 minus p is the probability of occurrence of the correct action. So 1 minus p cube is the probability for the first event, and the second event probability is p times 1 minus p square. As y can happen in any position, there are 3 possibilities, so into 3. So the overall probability is sum of these 2 terms, which is 1 minus 0.1 whole cube plus 3 times 0.1 times 1 minus 0.1 whole square, which is 0.9 whole cube plus 0.3 times 0.9 square, which is equal to 0.972. So in terms of percentages, 97.2% is the correct answer, which is option B. So in question 6 we are given a circuit where psi e is given, and according to psi in, what is the corresponding output to in question 6 we are given psi e, and we are asked to find what is the actual circuit is implementing when psi in is given and psi out is the output of the circuit. So psi e is given as square root of p times qubit 0 plus square root of 1 minus p times qubit 1. So assume that psi in is a times qubit 0 plus b times qubit 1. So actual input is psi in psi e. So the output is root p times plus b times 1 0 plus root 1 minus p times a 0 1 plus b 1 1. So in circuit we see that there is a conditional NOT gate where target is qubit in psi in. So output is root p times, the second qubit is control bit and the first qubit is target bit according to the circuit. So as we have second qubit in the first term as 0, the target bits does not change. But in second term we have control bits as 1, so target bits flips. Now we see that Now a measurement is done on second qubit. Measurement is done on second qubit. So if second bit happens to be 1 in the measurement, the output gets in the output, if the second bit measured is the second qubit measured turns out to be 1, then we see that input bit gets flipped in the output, otherwise we see that input does not change. So probability of bit flip is equal to probability of second qubit equal to 1, which is square plus root 1 minus p times b square, that is equal to 1 minus p a square plus b square, as a and b are coefficients of, as we see that a and b are coefficients of qubit 0 and qubit 1 respectively in sign state. So a square plus b square should be equal to 1. So probability of bit flip is 1 minus p. So the correct option is option B, which says a bit flip with probability 1 minus p. So let us look at question 7. Question 7. Let us look at question 7. In question 7, we are given similar circuit as in question 6, but psi e changes, where psi e is root p times qubit 0 minus root 1 minus p times qubit 1. So psi e in this question is root p times qubit 0 plus root 1 minus p times qubit 1. So taking psi in similarly as in previous question, we see that psi out is nothing but except a change in psi out in this problem is similar to psi out in the previous problem, except there is a sign change before the second term. So here is the output in the previous question, except a sign change here we have the same output. So output is root p times a 0 0 plus b 1 0 plus root 1 minus p times a 1 1 plus b 0 1. This is minus psi e in this question is root p times 0 minus root 1 minus p times 1. Considering psi in as in previous question, psi out is same as in previous question except a sign change before second term. Minus root 1 minus p. In the previous question, here we have plus sign, here we have minus sign, as psi e has a negative sign here. So, similarly we have measurement on second qubit now. Measurement on second qubit. We see that if the measurement on second qubit turns out to be qubit 1, we have a bit flip and also phase flip. So, as we have seen that probability of measurement on second qubit turns out to be 1 is 1 minus p in the previous question. With the same probability here we see a bit flip along with the phase flip. So, we have a bit flip and phase flip with probability 1 minus p. This is the probability with which the second qubit turns out to be 1 in the measurement. So, with the same probability we see a bit flip and phase flip in the psi in. Let us look at question 8. In the question 8 we are asked to find the minimum value of n, which will tell us exactly what the error has occurred in the qubit. In the lectures 33 and 34 we have dealt with Shor's 9 qubit code, which emphasizes that we need 9 qubits for efficient encoding and to tell exactly what the error has occurred. So, the correct answer to this question is 9, which is option D. So, let us look at question 9. In the question 9 we are given a state psi dash which is encoded form of psi, and is stated that there is a rotation of 60 degrees about x axis for the third qubit. So, the encoded state will appear as a linear combination of states where the third qubit has transformed due to a rotation of 60 degrees about x axis. So, psi dash is due to the rotation, the qubit 0 changes to, as there is a rotation of 60 degrees about x axis, theta changes to 60 cos theta by 2, which is cos 30 is root 3 by 2 plus e power I phi. Phi now changes to 90 degrees. So, I times sin 30, which is half, and qubit 1 changes to for example qubit 0 in the block sphere, qubit 0, this position is qubit 0, as there is a rotation of 60 degrees, say this is x and y. A rotation of 60 degrees. About x axis. So, the projection of the final state falls onto y axis, which means the angle phi is 90 degrees. So, we know that qubit can be represented in the block sphere in terms of theta and phi, which is cos theta by 2 plus e power I phi sin theta by 2 1. So, similarly following the same steps for qubit 1, we see that we obtains this particular state. So, the transformed state is 0 0, as 0 is transforms to root 3 by 2 0 plus I by 2 1, there is A, and B 1 1 as 1 transform to plus I root 3 by 2 1, which is equal to root 3 by 2. Taking root 3 by 2 as a common factor, we see that A 0 0 and root 3 by 2 as common factor, we get I times B 1 1 1, and next half as common factor, we have terms I A 0 0 1 and B 1 1 0. So, the correct answer is option D. So, let us look at question 10. In question 10, we are given a circuit where first we apply Harmat gate on first qubit, and then we have a C0 operation, and then we apply a Z gate, and again we have a C0 operation. So, Harmat gate is applied on first qubit initially. So, in the options we are given only 2 states possible. By looking at the options, we see that we need not take a linear combination of 0 and 1 for psi, but just consider psi as a pure state either 0 or 1. So, let us assume that psi is 0 in one case and psi equal to 1 in another case. So, the input is 0 0 0 and 1 0 0. Consider these two cases as separately. First, a Harmat gate is applied on first qubit, which gives us qubit 0 plus qubit 1 divided by root 2 times qubit 0 0, and here we obtain qubit 0 minus qubit 1 by root 2, and then there is a C0 operation and then we have a C0 operation where the target bit is second qubit and control bit is first qubit. So, this is control. So, the output is, as control bit is 0, this state does not change. As control bit is 1, target bit gets flipped 1 1 0. Similarly, here we obtain state 0 0 0 and then 1 1 0 divided by square root 2, and then we have a Z gate applied on second qubit. As the first state is 0 0 0, it does not get flipped. Z gate on second qubit, and the second qubit in the second state is 1, so it gets phase flip. The second case, we have a minus earlier, it turns out to plus, and then we have a C0 operation where first qubit is control and third qubit is target. So, as control bit is 0, this state does not get altered. As control bit is 1, the target bit gets flipped 1 1 1. Similarly, here as we have denoted this state as minus in our lectures and this state as plus, we see that qubit 0 0 0 transform to minus and qubit 1 0 0 transform to plus. So, the correct option is option B. In this assignment, we have dealt with problems on quantum error correction. Let us meet in the next week with a new topic. Here we end this assignment. In this week, we have discussed many quantum error correction techniques and coding techniques and shows 9-qubit code. Let us meet next week with a new topic in quantum information and computing. Here we end this assignment.